All right. Well, if you are in the room here and you can hear me, feel free to just type hello so that I know you can see me. Let me make sure that's working. Welcome to another session of live office hours. My name's Andrew. Um, if you are joining us now and you're in the room, feel free to introduce yourself. Say hello. I probably know you if you're here. Um, if you're here, it's probably because you've been in my class, you've seen me teach. I do this just to kind of open things up to everyone, and you can watch these after the fact as well. So if you have any GRE related questions, you can send those to me. Hey, Becca. You can send those to me at testprepstudios@gmail.com. I'll write that out here. Becca, you're the only one who sent me questions ahead of time, so it might just be you and me in this room here. But we'll get through these, and these are good ones that you sent. So I'll write my email here: testprepstudios@gmail.com. If you have any GRE questions that you want to see solved live, this is the place for it. So let's just dive right in here. Again, Becca sent me some great questions ahead of time that we'll walk through, and we'll start with this one. What is the least positive integer that is not a factor of 25 factorial? We'll talk about that, and is not a prime number. And then we have this list of numbers right here. Well, let's start with some definition, right? Definitions, vocab. An integer, of course, is a whole number. So 1, 2, 5, a billion. 3.7 is not an integer, right? We want an integer that is not a factor of 25 factorial. So let's talk about this. The factorial symbol, this exclamation point, what it's telling us to do is to multiply every number from 25 down to 1. So that would be 25 times 24 times 23 times 22 times 21, and on and on and on, all the way down to 3 times 2 times 1. So I'll state the obvious here, right? That's a big number. Huge. So big that we couldn't reasonably be expected to actually compute it. So here comes the kind of the heart of the matter. We're looking for an integer that is not a factor of 25 factorial. Well, what would be a factor of 25 factorial? 25 is a factor of 25 factorial. 24 is a factor of 25 factorial. 23 is, so is 22. Basically, any number in here is a factor of 25 factorial because I create 25 factorial by multiplying all those together. Becca, so far so good? And there's a little bit of a lag on the stream always. Just want to make sure we're okay. Great. Okay, so every number in here is a factor of 25 factorial. We're looking for the least, right? So we want to start with A and kind of work our way up. We can kind of go down the list here. Let's start with 26. Is 26 a factor of 25 factorial? Well, I don't see it in here, right? It's 25 times 24 times 23 times 22 times 21. I don't see it in here, but could I create 26 from any of the numbers that I'm multiplying together here? That's the question. And it's non-rhetorical. So yes or no. Could I create 26 using the component pieces that I have, that I've broken it up into? And if so, what numbers would create 26? Yeah. And which numbers would those be? Two and 13, right? Which definitely are in the mix here. There's a 2, and then somewhere in this ellipses is a 13. So we can say that 26 is a factor of 25 factorial, right? And for the record, this part, not a prime number, that's a little bit of a red herring because none of these are prime numbers. They're all even. Doesn't really make a difference. Okay, so let's go to 28. And Beck, I think you can probably see where this is going, but we'll just spell it out for anyone watching this on YouTube later on. For 28, could I create a 28? Well, sure I could. A 2 and a 14. Again, the 14 is somewhere in that mix there. 36. This one I might have to break down a little further. But actually, no. 18 and 2. Done. It's a factor of 25 factorial. 56. Well, that's going to be 28 and 2. 2 is a factor, but 28 isn't. But I could break 28 up even further. And so what this becomes is 14 times 2 times 2. I have a 2 right here. I have a 14 in here. And I have a bunch of other even numbers in here. So I'll very easily find another 2. So that's out. And then finally, 58 is what I'm left with. Becca, if I broke 58 down into its prime factorization, what do I get? What are the prime components of 58? 2 and 29. 29 times 2, right? I have a 2, as I've found in all these other ones, but I can't find a 29 in here. So if I were to divide this huge number, 25 factorial, by 58, I could cancel out a 2 on top and on bottom, but I wouldn't have anything to cancel out the 29. And therefore, it's not a factor of 25 factorial. And while I wait for the lag, I'll just say, Becca, let me know if that's all good, and if not, we'll move on to the next one. The takeaway from this, or such that it is break things down to primes. When you're dealing with huge numbers like this, breaking things down to primes is a very, very helpful exercise because, as I think I said this in the course, prime numbers are basically like the building blocks of any number. Any number can be broken down into its prime pieces. Okay, great. So that's a great segue into this next one right here. There we go. If n to the power of, or excuse me, n equals 2 to the power of 3, then n to the power of n is what? Well, n equals 2 to the power of 3, which is 8, right? So we're talking about 8 to the power of 8. And once again on this one, the trick is to break things down to primes. And that's a good habit to get into on any tough exponent problem, is to break it down to primes. So, Becca, what prime number can I break 8 down into? Or rather, what's the prime factorization of 8? Two times 2 times 2, aka 2 to the 3, right? So that's 2 to the 3 all to the power of 8. And my exponent rules, when I raise powers to powers, tell me that I'm going to multiply them. And so that's 2 to the 24. Boom. All right. So let me know if there are any issues with that. If not, I'm going to move on to one of my favorite questions. This is one of my all-time favorites. And it's not something that comes up, incredibly frequently. But when it does, knowing this trick is very, very helpful. Okay, so here's the trick. Well, let's read the question first. We got 1 over 2 to the 11 times 5 to the 17. Immediately, I think, way too big to do anything, by hand or anything like that. It's expressed as a terminating decimal. So what that means is if I divide 1 by this huge number, it's going to be 0.0000 something, right? The question is asking how many non-zero digits will the decimal have? So again, clearly I'm going to have, it's going to be 0.000 something, maybe 37521, right? This question is asking how many non-zero digits will I have at the end of this number? Okay, well, here's how to approach this. And again, it's a little bit gimmicky, and you kind of have to know the trick, but I'm telling you the trick right now, so you'll know it. This may seem like out of left field. What's the prime factorization of 10? If I break 10 down into its component pieces, what's the prime factorization? Two times 5. So let's put it this way. A 5 and a 2 make a 10, right? Anytime I have a 5 and a 2 and they match, we create a 10. So here's one way that I like to visualize it. Let's say we have a bunch of 2s floating around, 11 2s to be specific, right? On and on and on and on. And then I have a bunch of 5s floating around, 17 to be specific. I'm not going to write them all out here, but we get the idea. Here's my question. How many 10s can we create with these pieces? I think a good analogy here is chemistry. I hated chemistry, but one thing that I remember is like you have a bunch of like atoms or elements floating around, and they match up and create a molecule or a compound, whatever the difference is. But back to my question, how many 10s can I create if I have 11 2s floating around and 17 5s floating around? $11 of them, right? 2 is, what's that called? The limiting factor, limiting agent. Literally hate chemistry. So we have 11 2s, and we use 11 of these 5s, and of course there are 6 left over, to create 11 10s. Now, 10 to the power of 11 is 1 with 11 zeros tacked onto it, right? It's not a super interesting number. I'm going to erase all these. So just to kind of like catch up on everything that we have here, we have 1 over 10 to the 11. I matched 11 of these 2s and 11 of these 5s to each other. And then I have 5 to the 6 left over, right? Because there were 6 5s that I haven't used yet. Now let's look at this, right? 1 over 10 to the power of 11 is just going to be 0.00000000001. As I said, not an interesting number. The part that's going to give us the non-zero digits of this decimal is this. 1 divided by 5 to the 6. So, and just to be very clear with our math here, we could break this up into a multiplication, right? This is 1 over 10 to the 11 times 1 over 5 to the 6 to make things nice and easy. So what we have is 0.000001 times whatever the heck this number is, which is 0 point something else. And so here's the question. What is 1 over 5 to the 6? This is small enough that we can handle it on our calculator. 1 over 5 to the 6, or 25 times 25 times 25. Yeah, right? Whatever that is, 15,625. So 1 over 15,625, which we can type into our calculator, comes out to what? 1 over 15,000. 625. I got 0.000, so a few more zeros, and then 0.64 or 0.00000064. These are the digits that we're interested in. So there are two non-zero digits in this number once we write it all out. And you might say, like, how am I supposed to know that? Like, it's like magic. How did you know, like, how to do that? I mean, like, I've seen this question and other ones like it a million times. To the extent that there is any sort of red flag or tell that we're looking for, it's when you have a bunch of fives and a bunch of twos floating around together. Another similar version of this problem that I think I might have done on one of the YouTube or TikTok pages. It asks you how many zeros a particular number has. So it's like 3 to the power of, I'll write this in here because I don't think that's on the screen. Oops, sorry. It'll ask you like 3 to the power of 17 times 5 to the power of 4 times 2 to the power of 8, right? And just looking at this, if I look at the pieces that create zeros, as in create tens, fives and twos, I can create 4 tens because I have 4 fives and 4 of the twos. So anytime you got twos and fives floating around together, that creates tens. Okay. Here's a good one, talking about our units. So we have runner A going 4/5 of a kilometer. I'm going to write this as 0.8 kilometers versus 800 meters. Well, how many meters in a kilometer? You know, I'm trying to remember on the test because this looks like it was from Manhattan. Is it from Manhattan, Becca? I don't think this is an official question. I think on the test they might even give you the conversion ratio. Oh, okay, yeah. So no worries. You had this one already. I'll just finish it out since we brought it up. Yeah. The way to solve this, of course, since we're talking about kilometers, there are 1,000 meters in every kilometer, so we would need to multiply this by 1,000. 1, 2, 3, and that gives us 800 meters so that they're equal. Great. No worries. Ooh, this one looks fun. The certain train. And I'll ask you, Becca, since again we're like the only ones here. What type of question is this that we talked about in the course? When I look at this question and particularly look at the answer options, what type of question am I talking about? Oops. Converting a word problem. Yeah, so it is a word problem. What I'm getting at, in sort of a roundabout way, is the fact that we have variables in the question and variables in the answer options. And this happens all the time on the GRE. GRE loves these kind of questions because you can solve them without algebra. And how do we solve them without algebra? Well, we pick our own numbers. So let's just pick some numbers to go in for S, T, and Y. And if it bugs you that that we can just willy-nilly pick numbers like this, consider this. The problem is written in such a vague way, right? It's completely open-ended. So if you pick numbers to plug in for those vague variables, as long as you aren't picking, negative numbers, we can't travel back in time or anything. Any number should work. Any number should make this true. So I'm just going to say that S equals, how many miles? The train travels 40 miles in 5 hours. T is 5. The question is, how many hours is it going to take the train to travel Y miles? And again, we can just make this up. Why don't we say 120 miles? And you might say like, well, how do I know what numbers are good to pick? Literally any number is fine. Any numbers are fine here. I mean, I kind of peeked ahead and saw where this was going and thought it might be nice to divide by whole numbers and rather than get decimals, but any number you pick, this will work. There's one little exception to that that we'll talk about at the very end of the problem. But let's go with this. So we've decided that the train travels 40 miles in 8 hours. If we're going to do our DRT calculation here, that means the train is going 8 miles an hour. We want to know how far the train will travel in 120 miles. Well, if the train can travel 40 miles in 5 hours, then it's going to take how many hours to go 120 miles? And this is just a proportion that we'll set up, right? And everyone kind of does proportions in their own way. So you don't have to do it this way if it doesn't make much sense to you. But you could look at this and say, okay, we went 3 times as many miles, so we're going to take 3 times as long. So 15 is the answer to this question. Now the last step is to plug the numbers that you chose into the problem, wherever you see S, Y, T, et cetera, and see which one gives you 15. So let's start with answer option A. S times Y, 40 times 120, what's that, 4,800 divided by 5 is not 15. Not sure what it equals, but it's way bigger than 15. S times T, what's that, 200, excuse me, yeah, 200 divided by 120. What do we get? 1.6666. T times Y, 120 times 5, divided by 40, gives us 15. So this one's looking good. We're going to double check the last two just to make sure there's not a duplicate answer. That happens on rare occasions. S divided by T times Y, well, already that's going to be a decimal, right? 40 divided by 120 times 5, way too small. And then S plus Y, so what is that? 160 divided by 5? Divided by 5, 32. No. So the beauty of that is that you don't have to do any thinking, or much thinking, I'll say. The real thinking comes in just picking your numbers, which, as I said, you can just pick out of a hat. You have to understand the relationship between distance, rate, and time, right? That's the one little piece here. But as long as you can do a distance, rate, time setup, you're okay. And I'll talk a little more, Becca, and if you have any questions, feel free to type them in the chat. Here's the one little warning that I'll say about these problems. There are some numbers you generally want to avoid picking. 0 and 1. If you're dealing with this type of problem, I would avoid choosing 0 and 1 because 0 and 1 have particular identities, or excuse me, properties. 1 is the identity property, which is if I multiply anything by 1, it remains the same. And 0 has the property that if I multiply anything by 0, it becomes 0. So it's not super helpful to pick 0 here because if I plug 0 in for S, A, B, D, and D are all the same. Okay, great. Let's keep going here. This one. This is a fun little probability question. And it all hinges on one word or one concept. Mutual exclusivity. Becca, what does it mean if outcomes are mutually exclusive? Good to talk about this. Mutually exclusive outcomes. if one outcome occurs, then the other possible outcome cannot occur. Right. And so one particular example of this would be the rules of a dice, right? I can't roll a 1 and a 6 on the same roll. A die only has, a die can only have one roll at the same time. So when we say that these outcomes are mutually exclusive, it means that let's call them A, B, and C. The risk of creating more variables in here, but we'll call them A, B, and C. Outcome 1, 2, and 3, A, B, C. Outcome A can't happen at the same time as outcome B. Now, as I said, there are some examples of this that we're very familiar with. Rolling a dice, flipping a coin. I can't flip heads and a tail at the same time. But what we might not be used to is cases where it's a little lopsided, right? On the roll of a die and the flip of a coin, there's equal outcomes for all possibilities. What's different here, of course, is that there are 3 different weighted outcomes. But let's go. I'm using a die as our kind of like guiding example for this. The probability of rolling a 1 on a fair 6-sided die is 1 out of 6. The probability of rolling a 2 is 1 out of 6. 3, 1 out of 6. 4, 1 out of 6. 5, 1 out of 6. And 6, 1 out of 6. If I were to add up all these probabilities, what would I get? What would I get? Oops, sorry. What would I get if I added up all those probabilities? 6 out of 6 or 1, i.e., it is 100% certain that the die will land on one of the faces, right? And so going back to this problem, I know that's a little bit of a long intro, but going back to this problem, we have this experiment, roll of a die, that has 3 possible outcomes, A, B, and C. There are 3 different probabilities, but they're mutually exclusive. So if I were to add all these probabilities together, they would have to equal 1. There are only 3 possible outcomes. There aren't any other outcomes besides these 3. They're mutually exclusive. Therefore, when I add them all together, they have to equal 1. And so all I have to do at this point is solve for 1, or solve for P. And I can do that by multiplying both sides by 4. So I'll do that. That becomes 2. That goes away, and that becomes 4. And then I get 4P plus 2P plus P, so 7P equals 4. P equals 4 over 7. Yep. Great. Great. Mutual exclusivity. That's the buzzword on this one. All right. So we got daily low temperatures and talking about the range. And I'm going to, well, that word that's cut off there is just low, L-O-W. Daily low temperatures during July 2012 was 25 degrees Fahrenheit. Again, we'll start with the definition here. Oh, sorry, yeah, Becca. Back to the probability one. There it is. All good. Great. So going down to this one here, we got a range of temperatures. What's the definition of range when we're dealing with a set of numbers? Skip this one. Great. I'll come back to this at the end. Oh, this is a good one. odds and evens. So I'll give you just a second to read it over if you've never seen this before. And we'll start with this. I know nothing about y, right? Aside from the fact that it's an integer. Could be odd, could be even. Has to be one or the other. Those are mutually exclusive outcomes, by the way, right? Odd and even. Y has to be odd. 69 is an odd number, but 50 times y, an even times any number, is going to be an even. Right? So what I have is an even plus an odd. Slow me down if it's going too fast or if anything's not making sense. So an even plus an odd. And an even plus an odd has to be an odd. And we can test that out with any example that we want, right? 2 plus 3, 58 plus 7. So no matter what, that's going to be an odd number. What was I saying here? Yeah. So now all we have to do is look at this, right? These ones. Again, I don't know anything about y, but I know that x is an odd number. So an odd times some other number depends. Could be even, could be odd. This is a must be true situation. So that could be even, that could be odd. An odd number plus an unknown number, again, I don't know. Could be odd, could be even. But an odd number plus an even number, this has to be even, right? 2y must be an even number no matter what y is. Well, that has to be odd. And then just to finish this out, right? This is an odd times an odd. So an odd minus 1, well, that's even. So that must be even. And same deal here. An odd plus an odd is an even. So let me know if there are any issues on that one. But this just comes down to plugging and chugging. And I'll just say this, there are no exceptions to odds and evens. So if you forget the rule, if you some people like to remember the rules, even plus an even is an even plus an odd is an odd plus an odd, right? You can always just quickly test it with 2 and 3 if you ever forget the rule. It's just as true for 2 and 3 as it is for 2002 and 2003. All right. So here's one that is good, and it looks like it got a little cut off. Sorry if the noteboard's bouncing around a little bit. Let me zoom out on this one. Okay. So we got this sequence, B1, B2, B3, all the way up to B100. The kth term, whatever that means, is defined by B sub k is equal to 1 over k minus 1 over k plus 1. Now, the first hiccup might be this notation, right? You may have no idea what this is even saying. Let me try to illustrate with an example. What this is saying is that the first term would be 1 over 1 minus 1 over 1 plus 1. The second term would be 1 over 2 minus 1 over, okay, plus 1, that should be in black. 1 over 2 plus 1. The third term should be 1 over 3, last one, I promise, minus 1 over 3 plus 1, red, 3 plus 1, and on and on and on. So that on its own might be a hard part for you, getting that set up. But once we understand the mechanics of this, there's a very, very quick way to do it, and I'll show you what it is. Let's start with this. I always try to eliminate answer options first before I show you kind of the quick way to do it. And I'll erase this just so we have a little room to breathe. What is the first term? What is b of b sub 1 when I actually plug this in? Well, it's 1 over 1 minus 1 over 2, right? Or 1 minus 1/2, or 1/2. Now, this question is asking for the sum of all the terms. The second term, every time the next term is going to be a little smaller, but the sum of all these terms together, if I add this to the next one, to the next one, to the next one, has to be greater than 1/2, right? I'm not losing any ground. I'm just adding a little bit every time. Let me know if I've lost you at this point, because this question is kind of tough. But as a first kind of pass, what we can say is, all right, the answer has to be greater than 1/2, because b of 1, or b sub 1, is 1/2, and I'm only going to be adding numbers to it. And what does that mean? Well, that means we can get rid of A, B, and C right there, right off the bat. And then it comes down to these two, which are so close together. I mean, 100 divided by 101 and 1, which is basically 101 over 101, are 1/100th, 1% apart. All right, so enough of this. Let's actually solve this problem. Here's the trick. And when you're dealing with a set of numbers this large, 100 numbers, huge set of numbers, there's always going to be some pattern. Watch this, and I'm gonna try and find a kind of a bigger space to work with. Okay, I'm gonna move this over just a little bit here. So the first term, oh, where did that go? The first term is 1 over 1 minus 1 over 2. The second term is going to be 1 over 2 minus 1 over 2 plus 1, or 3. The third term is going to be 1 over 3 minus 1 over 3 plus 1, or 1 over 4. And on and on and on. And when I add these all together, at every step, chop, 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 this is going to happen over and over again, right? The positive version of it is going to cancel out with the negative version of it. Oh, and sorry, I'm going to bring that up a little bit, because that doesn't seem to be showing there. There we go. At every step, the positive piece is going to cancel out with the negative piece. And this is going to happen again and again and again up until the very last part of this, which I'll bring over here. What's the very last term that we plug in? B sub 100. So that's going to be 1 over 100 plus 1 over 101. Well, all of these numbers will have canceled out with each other, including that one. And what I'm left with is 1 over 1, sorry, that's a minus. 1 over 1 minus 1 over 101. And if I use my fraction rules, right, I create this into 101 over, oh, sorry, I keep forgetting that doesn't show up there. Let me know if you're having any issues seeing this. I'll bring this down a little bit, right there. So what I'm left with from the top is 1, or 1 over 1. And what I'm left with on the bottom is negative 101. So it's just going to be 1, or 101 over 101, minus 1 over 101, and that comes out to 100 over 101. That is a tough one. And let me know, Becca, if any part of that you need to go back over. If not, we'll keep going here. So we've moved, and this is the last one here. We've moved from the land of must be true to the land of could be true. And could be true problems are, at least all else equal, easier, I would say easier to prove, because all we need to do is come up with one example, right? One example of it being true. So we'll go, we'll go down the line here. And if we can find one example of each of these being true, then it's an example that it's proof that it could be true. So let's do this. We'll start with x equal y. Is it possible for x to equal y? Well, no, because if we look at x and y by themselves, if we look at x and y by themselves, which we're totally allowed to do, right? We can just say 3x is less than 2y and forget about z for just a second. Is it possible for 3 times something to be less than 2 times the same thing? If they're negative, yes, but they're not negative, right? They're positive. They have to be positive, meaning that this one cannot be true. Is it possible for y to equal z? Well, let's find out. We'll just look at this one in isolation. 2y is less than 4z. 2y is less than 4z. Let's make our life a little easy. Divide both sides by 2, right? So that we get y is less than 2z. Is it possible for this to be true and still have this be true? Absolutely it is. Take the number 3. 3 is less than 6. Works for me. All we need is one example, and then we're good. So that's okay. Y is less than z. Oh, sorry, greater than z. Is that possible? So here's where it might get a little more difficult. We'll use this same inequality here. Is it possible for a number to be less than, for a number to be greater than another number and be less than 2 times what it is? And for this one, let's say that y equals 4 and z equals 3. Y is greater than z in this case. But if we plugged it in here, 4 is indeed less than 6. So I have my example, my one example that I need. And then for this last one, is it possible for x to be greater than z? Well, let's look at x and z in isolation. We'll take 3x and 4z. What we know is that 3x is less than 4z. Doesn't matter that there's a 2y in between them. That's neither here nor there. Is it possible for x to be greater than z and still have this be true? Well, let's find out, or try to find out. What if x were, we'll use the same numbers, 4 and 3. So x equals 4 and z equals 3. Is 12 less than 12? No, it's not, right? 12 is not less than 12. But that's only one test that we did. We can try and find another one. What if we did, what if we did 101 and 100, right? Numbers that are very close together. If this is true, if 100 is greater than 101, could this still be true? Well, we would have 303 is less than 400. That's 400. Yep. And that is a true statement. So this one should be true. Oh, and this I was just making sure this wasn't the correct answer, right? This was your answer, Becca. So correct answer should be these three. But let me know if the answer key says something different. Shouldn't. I'm just going to make super sure here. X, Y, and Z are positive numbers. Like that. There it is. Oops. There we go. Oh, this is a different format of it. Yep, great. B, C, and D. Awesome. And so that does it for the ones that Becca sent. Again, if you're watching this after the fact on the YouTube channel, feel free to shoot me a message at the email address below, testprepstudios@gmail.com. The next live course is not on the book. Oh, Becca has another one. Yeah, so we'll take a look at this other one. The next live course is not on the books quite yet, so don't know when it's going to run. Gets a little tricky with the holidays, but looking at probably January of next year. So let's see here. Look at this. So we got this other one here. What is the No, that was the one that we saw before. There we go. Ooh, that looks like a fun one. Integer v is. I'm gonna copy this into the board. Sorry if the board bounces around for a second. It tends to do that. Okay, let's see here. Nope. It won't let me put a screenshot in. That's annoying. Let's do this. Give me 1 second. Export this as a PDF. Problem. Open it as a PDF. It's on its side, so we'll rotate. Come on. There we go. All right. Okay, here we go. So, the integer v is greater than 1. If v is the square of an integer, which of the following must also be the square of an integer? Ooh, gonna have to dip a little into quadratics for this one, I think. There's probably a better way to solve it that I'm not seeing. So, and let me just get rid of some of this clutter here. There it is. That's that. Where's my stream? There we go. Okay. So let's start by thinking of some examples of a square of an integer. 81 is the square of an integer. 25 is the square of an integer. 49 is the square of an integer. 36, right? These are all squares of integers. And we want to know which of these is also the square of an integer. Well, let's start with the easy one, right? A. 81 times v. Now we know that v is the square of an integer, meaning that the square root of v is an integer. So the question is this whole expression the square of an integer? Well, if I know my radical rules, right? Radical rules say that the square root of a times b is equal to the square root of a times the square root of b. So 9 times the square root of v. V is an integer, and so is 9, and so this is an integer, right? We're looking for all answers that could be true. All right, now, I think the best way to go about this, aside from like quadratic factoring, which we can explore in a minute, but I think the best way would be to test some numbers. And we'd start with the smallest possible value of v. What is the smallest possible value of v? What is the smallest possible value of v here? It's 4, right? Because v has to be greater, the integer is greater than 1. And so the smallest possible value is v. Well, if v is 4, then this becomes what? 100 plus 20 plus 1, or 121, right? What would the next smallest one be? It would be 9, right? And then that's 25 times 9. Let me see this. 25 times 9 plus 30 plus 1, 256. So if I plug in, when I plug in 4 for v, I got what? 121, which is 11 squared. When I plugged in 9 for v, I got 256, which is 16 squared. Is that right? Yeah, 256 is 16 squared. When I plug in the next one up, which is 16, that's 16 times 25, 400, plus 40 plus 1. I get 441, unless I did some math wrong. I square root that. Yep, the square root of 21. 441. Now, after I do this 3 or 4 times, I'm pretty confident that something interesting is going on. And if you aren't okay with quadratics, that's about as far as you can take it, right? 2 or 3 tests. Maybe you try a really wild one like, I don't know, 49 or 81 or something, see what happens. But after you've tested this a few times and you see that it keeps coming out to a perfect square, it might be worth going. Here's the way to do this in sort of a quadratic factoring way. And I know we might have touched on quadratic factoring very briefly, but here's what it is. V is the square of an integer. Let's call it x squared, right? V is the square root of an integer. So what I could say this is 25 x squared plus 10x plus 1. 25x squared plus 10x plus 1, if I rewrite that out. And I could then, if I wanted to, factor this into something where the last terms multiply to 1, and the first terms multiply to 25x squared. So 5x and 5x. And to double check this, I would FOIL it, right? I get, 25x squared, first, outer, plus 5x, inner, plus 5x, and last, 1. And sure enough, that comes out to 25x squared plus 10x plus 1. Well, this number right here is a square. It's 5x plus 1 squared. Oh, I'm sorry about that. I'm so sorry. I was talking all that time there. Yeah, let me do this. So sorry about that. Didn't see that chat there. The idea, what I'm getting at is if you rewrite this in a quadratic form as 25x squared plus 10x plus 1, that factors into 5x plus 1 times 5x plus 1, i.e. 5x plus 1 squared, which is a perfect square. The same idea applies on this next one here. So again, we'll call v is x squared. So that would mean that 4v squared would be 4x to the 4 plus 4x plus 1. And in this case, again, it would just be 2x squared plus 1 times 2x squared plus 1, which is a perfect square. It's this times itself. 2x squared plus 1 squared. And so all three of these are perfect squares. Bring that a little further down. But realistically, so there's like called the pure math way to do it, which we just did, right, with quadratics. My suggestion for this one would be to test 3, maybe even 4 numbers, and the minute you see it keeps coming out to a perfect square, accept that as enough. Because the algebra on this one is brutal. All right. Any other questions? Any follow-ups on this? Of course. Great. Well, as I said, if you're watching this afterward, drop me a line. Let me know. Great. Let me know if there are any other questions you want to see for the next time. My hope is to make this a regular thing, maybe once every other week or so. But that does it for us today. Thank you very much. Thanks, Becca. Take care, everyone. Yep.